on yesterday, but let's say I give you an example, and I said, um, given that f of x equals 6 and g of x equals 4 times the natural log of 3 minus x. And I said find the area between f and g and the line, or f and g, the y-axis, and the line x equals 2. So if we had to do that, what we would do on this is we'd go through and we'd say, okay, if we graph this, you'd have a line, you'd have the y-axis, you'd have the x-axis, and you got the line goes across here. That's the line y equals 6, so that's f of x. And you have another curve, kind of goes down like this, and that curve, that's g of x. So we'll call that g of x. And then you got the region, you got the y-axis, which is right here. You got the line x equals 2. So if you were going to calculate this region, that would be this region right here. And if I wanted to calculate that, what I could do is I'd have to have a calculator for it because this isn't the easiest thing to integrate. But I'd integrate from 0 to 2. The top curve, which is 6, minus the bottom curve. And the bottom curve of this thing is 4 times the natural log of 3 minus x. And then I'd have dx. And I get the area of that in between there. So that's the top curve minus the bottom curve. And that's pretty standard on what we did yesterday. But what if we did the same, we had the same region? So, but I asked it a little different. What if I asked it like this? Using the same region, find the volume where the known cross sections perpendicular to the x-axis are squares. You might go, wow, that's pretty intimidating. Okay, so we got the same region, but now we're going to look at, well, what happens if we do cross sections perpendicular to the x-axis are squares, and we're trying to find the volume. So here's what you're going to do. And then I'll generalize it for you. So you got this thing here, you got the x-axis, you got the y-axis, you got this line, you got this, and you got this. And so you got this region right here. Okay? But I'm going to draw it in a little different way. And what I'm going to do is I'm going to try to draw it in 3 dimensions. So what I mean by that is I'm going to draw an angle down here. And let me do that. Let me just draw them straight. So Draw this down. Draw x-axis out this way. So this is the y-axis. This is the x-axis. Okay. And if we draw the lines here, the line y equals 6 is going to come out like this. We draw the other one, it goes like this. That's the natural log one. So that's y equals the natural log. Sorry, 4 times, what is it, 4 times the natural log? Let me write it here where I can get to it. Y equals 4 times the natural log of 3 minus x. And then we have the line y equals 2, so that'll define our region. Our x equals 2 right there. This is 2. So we got this region. But what you have to kind of think about is now these are going to be squares that are coming straight out at us that have some kind of dimension. So think about this as kind of being like tiles. So if I drew one right here, it might go up like this, over like this, so something like that. If I drew one right about here, go over like that, kind of come up here. So I'm trying to make this look as three-dimensional as possible. And if I had it here, maybe I'd come up here, go over here, and then down. So something along those lines. And you'd have this three-dimensional shape, right? It would kind of go like this. And you can think about that thing coming right out of the screen at you. Now, one of the important pieces is these are like tiles. So let's say these are like tiles and these are cross sections. What we'd have is we'd have some sort of a width to this tile. So this tile would have some kind of a width. And we could find, and that width has some sort of a change in x. We'll call it dx, because remember that's the x-axis. So that width right there is some sort of a change in x. And I guess that tile actually kind of goes like that. Okay. So you got this tile. It looks like that. And if we wanted to find the volume of just that one tile, let's say we wanted to find the volume of just that one tile, notice that this shape right here is a square. That shape of that one tile is a square. And so if we wanted to find the volume of that one square, what we could do is the volume of that one square would be the area of that square. Well, think about the area of that square. The area of that square would be the top curve minus the bottom curve. And then squared, because this side is equal to the top minus the bottom. So that's the area of the square. Well, if we wanted to find the volume of that tile, the volume of that tile would be the area of that square times the width of that square, which is dx. Well, that would just give you that one tile. What if we wanted all of the tiles in there? We wanted to add up all the tiles that we had in there. Well, you hopefully can kind of see where I'm going with this. What I'd have in that case is I would have the integral from 0 to 2, because that defines our region. And then we'd have the volume of one tile. Which is the area of the square of one of those tiles times the width of that tile. Now, then we'd use the calculator to solve this. So that's if the cross-section perpendicular to the x-axis are squares, and that's the kind of problem that you're going to have. The main idea, the general idea, so in general, the volume of a known cross-section, so known cross-section meaning a rectangle, a square, a semicircle, or a triangle, the volume of a known cross-section of a region perpendicular to the x-axis from x equals a to x equals b is found by the following. What we would do is we would integrate from a to b the area formula, area of the cross-section, times dx, or dx is the width of the cross-section. That generates the volume of the known cross-section. I'm going to stop there because it's a pretty long video and let you try some problems, and then if you struggle with them, then let's work some of them out together. Okay, but today's assignment just deals with rectangles and squares. If you have questions, let me know.